Alright, welcome. Going to cover section 5.1, right triangle trigonometry. Sorry I was not able to record the class session yesterday due to my computer being close to dead. So we'll get started. So, chapter 4, specifically section 4.2, is all about defining sine, cosine, and tangent as the x and y coordinates on a unit circle that correspond to a given angle. And then section 5.1 is going to take a right triangle approach to trigonometry. So if you look down at the figure, okay, let me actually make this larger as well. Okay, so down here in the figure, you can see figure 5.4, the triangle on the left. You form a right angle. The side opposite the right angle is called the hypotenuse, and the other two sides are called the legs. But in part B of the figure, if you look, if we label the bottom left angle with an angle theta, we can now call the legs the adjacent and opposite sides with reference to that angle. So the side that is touching the angle itself is called the adjacent side, and the side that is opposite the angle is called the opposite side, which is just labeled op. Okay. Now, using the triangle on the right side of the figure, we can now define sine, cosine, and tangent of the angle. Okay, and actually, as a matter of fact, I must fix the handout. Okay, so sine, cosine, and tangent. Now, sine of theta is going to be defined to be the length of the opposite side over the length of the hypotenuse. Cosine theta is defined to be the length of the adjacent side over the hypotenuse, and tangent of theta is defined to be the length of the opposite side over the length of the adjacent side. Okay, so some of you might have seen a mnemonic to help you remember this. So SOHCAHTOA, and that's read SOHCAHTOA. So the first three letters are telling you that for sine of an angle, the value is the opposite over the hypotenuse. For cosine, it's adjacent over hypotenuse, and for tangent, it's opposite over adjacent. Okay, so now let's take a look at an example. Okay, so example 1, find the exact values of sine theta, cosine theta, tangent theta when the adjacent side corresponding to the angle is 4 and the hypotenuse is 7. Okay, so first thing, now that we know what we're looking for, we can go ahead and draw a right triangle, and we'll label that with the given information. So here's my right angle and my right triangle, and we were told that actually I don't like my triangle. Let me make it look more like a right angle here. There we go. Okay, so we were told, well, first of all, I would label the angle in the bottom left. So we were told the adjacent side has length 4, the hypotenuse has length 7, and what we really don't know is the length of the opposite side. Okay, so before we find sine theta, cosine theta, tangent theta, let's go ahead and use the Pythagorean theorem to find the length of the opposite side. Okay, so what we know is we know that the sum of the squares of the legs, so op squared plus 4 squared, is going to end up equaling 7 squared. This tells us that op squared is equal to 49 minus 16. We're going to get 33. So the length of the opposite side is now square root 33. Typically you have, excuse me, typically you'd have a plus or minus on the right hand side, but since we're talking about the length of the side of a triangle, we will take the positive root 33. Okay, and then from here we can now get sine theta, cosine theta, and tangent theta. So sine theta is going to be the length of the opposite side of the angle over the hypotenuse, so you get root 33 over 7. Cosine theta is going to be the length of the adjacent side over the opposite, or sorry, over the hypotenuse. And then I ran out of room, but now tangent of theta is going to be the length of the opposite side over the length of the adjacent. We get root 33 over 4. Okay, and then in later problems we might use one of these three expressions to actually recover the angle itself, using arcsine, arccosine, or arctangent. Okay, so next example, we're going to find tangent of 32 degrees and sketch a right triangle with a 32 degree angle. Now if you read in the textbook, there's lots of right triangles that have a 32 degree angle. Okay, and it turns out that if all the angles in a right triangle are the same, the ratio of the sides will be the same in those triangles. Okay, so I'll kind of show you this with a quick example. So first of all, tangent of 32 degrees. You can get out your calculator and I'll round this to 2 decimal places. Make sure your calculator is in degree mode. And to 2 decimals I get 0.62. Okay, now you can view this fraction, or you can view this as a fraction in 2 ways. One is I can just take my 0.62 and divide by 1. The other is that 0.62 is also the same as 62 over 100. So that'll at least let me create 2 right triangles. So there's my 32 degree angle. Since tangent is opposite over adjacent, this is the reason I wrote the value as fractions. One right triangle could have the opposite side as 0.62 and the adjacent side as 1. Or, now that I've also written 0.62 over 1 as 62 over 100, okay, you could also have another triangle with a 32 degree angle where the opposite side is 62 and the adjacent side is 100. Okay, so this is all really similar triangles would be saying is, so these are both 2 right triangles that would have the same angle measures inside, and the ratio of opposite over adjacent is the same in both triangles. Okay, so there's lots of right triangles. There's actually infinitely many right triangles that have a 32 degree angle, but these are just 2 that could arise. Okay, now we can also use triangle trigonometry to find an angle of a triangle. So let me just draw, in class I just drew a triangle. Draw it down here. And I think what I did was I said, okay, maybe this angle is 40 degrees. Oh gosh. Okay, so maybe this is a triangle with a 40 degree angle in the bottom left. Geez, I just cannot draw a degree symbol today. There we go. So we got a 40 degree angle. We'll say the length of the base of this triangle, I'll just make something up, is 32. And then let's just say that the length of this other side here is 20. And we're going to find the area of this triangle. Okay, now in general, the area of a triangle, notice this is not going to end up being a right triangle, it's always 1/2 the base times the height. Okay, now the height, I'll draw, maybe I'll just change colors here to red. Okay, so here's going to be my height h of this of this non-right triangle. Okay, so now the formula for the area is going to be 1/2 times the base, which is 32, times this value of h. Okay, so we're going to have to use some triangle trigonometry to find this value. Now be careful because the height h is not, it looks like it's about half of 32, but that's just because of how I've drawn the picture. Okay, now what we're going to do is we're going to now realize that we have now created a right triangle where the angle in the bottom left is 40 degrees. We do not know the length of the adjacent side. The opposite side has length h. In the hypotenuse, it has length 20. So we need to apply a trig function to this angle of 40 degrees. The trig function that's going to relate the height, or the opposite side, to the hypotenuse. And one such trig function that's going to do that for us is if we apply sine to this 40 degree angle, it's going to be the length of the opposite side h over the length of the hypotenuse, which I labeled as 20. Okay, and this is going to imply that h is equal to 20 sine of 40 degrees. Okay, which is approximately, if I round it to 2 decimal, well, let's do this. Instead of doing my rounding at this step, I'll just use that value of h and come back up here to my area equation. This is 1/2 times 32 times 20 sine of 40 degrees. And this value, I'll plug that in my calculator. And that is approximately 205.69. So that would be the area of this triangle rounded to 2 decimal places. Okay. Now, we can also define the reciprocal trig functions. We know SOHCAHTOA. We know if you have an angle and a right triangle, sine, cosine, and tangent are defined as previously. Now, cosecant theta, secant theta, and cotangent theta, those are just the reciprocals of sine, cosine, and tangent. So if I want to find secant theta, cosecant, and cotangent, if we know tangent of theta is 1/4, and theta is an acute angle in a right triangle. So I'm going to draw that picture over here on the side. Oops, I did not mean to highlight that. There we go. Okay, so here is my right triangle. Here's my angle theta. And since tangent theta is 1/4, I can treat the opposite side as length 1 and the adjacent side as length 4. And then, since 4 squared plus 1 squared is 17, you could take the square root of that to find the length of the hypotenuse. So that's coming from Pythagorean theorem. You might want to verify that. And then we'll do cotangent first. Cotangent of theta, since tangent's 1/4, cotangent is just the reciprocal of 4. And then secant theta is, well, cosine of theta was adjacent over hypotenuse. So secant theta is going to be the length of the hypotenuse over the adjacent side. And finally, cosecant theta. Sine is opposite over hypotenuse, which would be 1 over root 17. Cosecant theta is the hypotenuse over the opposite side. You're just going to get root 17 divided by 1, or just root 17. And again, we could find the angle if we wanted to. We could use the expression tangent theta equals 1/4 and just apply arctangent to 1/4 to find the angle. But we'll save that for one of our next examples. Okay, so again, with a right triangle, which I can draw over here to the right. If I call this angle theta, that's our right angle. That's the adjacent side to the angle. That's the opposite. This is the hypotenuse. Well, since sine theta is opposite over hypotenuse, that means that the angle theta can be recovered by applying arcsine to the opposite side over the hypotenuse. Okay, and the same would be true for arccosine or arctangent. Okay, so make sure you look at this definition. And the opposite and adjacent sides are always going to be positive and less than the hypotenuse. So at the bottom of that box, opposite over hypotenuse will always be between 0 and 1. Adjacent over hypotenuse will be between 0 and 1. And then opposite over adjacent will always be greater than 0. And if it's an acute triangle, that just means the angle theta will be between 0 and 90 degrees. Okay, so we take a look at this example now. So we're going to be illuminating a flag, a spotlight that is horizontally 25 feet from a flagpole is used to illuminate a flag flying at a height of 16 feet. And at what angle above the horizontal, called the angle of elevation, must the spotlight be aimed? Okay. So first of all, I'll draw my terrible picture here of a spotlight. And that spotlight is supposed to be 25 feet from a flagpole that is 16 feet tall. And then what we're trying to do, let me grab red for the hypotenuse, so we want to angle this spotlight so it would illuminate the flag. Okay. Now what we can do is the angle that's formed on from the horizontal, we can call that theta, and we're trying to find this angle in degrees. Now what you'll notice first is that we have an angle, and we know now, if you see this little right triangle that I've formed, we know that the opposite side of the angle is 16 and the adjacent side is 25. So what you'll first maybe think of doing is what trig function can be applied to that angle to get a relationship between the sides, and that would be tangent theta. Tangent theta would give you 16 over 25. And then if you rewrite that in terms of arctangent, the angle theta would just be arctangent of 16 over 25. And I've run out of room here, but let me actually rewrite this somewhere else. So theta is going to be arctan 16/25. And then I'll round that to 2 decimal places. I'll get my calculator out, make sure you're in degree mode. Hit the tangent inverse button. And you will see that you get 32.62 degrees. Okay. So that would be the angle of elevation, the angle above the horizontal you would need so that the spotlight would illuminate the flag. Okay, and this is the last example we got to in class. We had about 9-10 minutes left. I gave everybody a chance to work on this problem or work on this together or individually. I came around the room and checked how people were doing, but I will spend the last 5-10 minutes or so of this video doing these problems. Okay, so we're going to solve each of the following right triangles, which means find all other sides and all other angles. Now, first thing I want to do is, in any triangle, doesn't necessarily need to be in a right triangle, but specifically in a right triangle, if I call the bottom left angle theta, in the top right angle phi, all 3 sides in any triangle have to add up to 180. Since there's already a 90-degree angle in the bottom right, theta plus phi will end up having to be 90 degrees. Okay, so once you use an inverse trig function to find theta, you can just take 90 minus theta to find the other missing angle. Okay, so coming down here for part A, I'll draw a picture of the triangle given. So here's the angle theta, that's 26 degrees. I'll call this other angle phi, and we know the hypotenuse is 8. Okay, so first of all, phi is going to be 90 degrees minus 26 degrees, and we end up getting 64 degrees. Okay, so now we know that other angle, and I'll label these as adjacent and op. Now I need to find the length of the opposite side and the adjacent side. Okay, so first of all, if I want to solve for the opposite side, since the hypotenuse is known, I can just now apply sine to this 26-degree angle, which would be the length of the opposite side over the hypotenuse. So that tells me the length of the opposite side is 8 sine of 26 degrees. And then using our calculator to approximate to 2 decimal places, I get 3.51. Okay, so there's the length of the opposite side. And then maybe I'll write it over here, but if I want to find the length of the adjacent side, I can apply cosine to that 26-degree angle to get adjacent over 8. So the coming down here, the adjacent side is going to be 8 cosine of 26 degrees, which is approximately 7.19. Oops. Okay, so now the other missing angle was 64 degrees, the length of the opposite side was 3.51, and the adjacent side had length 7.19. So here's all my 3 missing values. Now, we're going to cover part B in class today. I'll leave it to everybody as an exercise. This time you're given the adjacent side and the opposite side. You have to go through and find the hypotenuse, either using tangent, or you could, well, you probably don't want to use tangent, but in part B you have the adjacent and the opposite side. You can use the Pythagorean theorem to find the length of the hypotenuse, and then you can use tangent of theta, which is opposite over adjacent, to find the angle theta, and then just take 90 minus theta to find the other missing angle. Okay, so if anybody has any questions, make sure to get a hold of me through email or the TLC during my office hours. Hopefully everybody thinks this, or finds this section a bit more straightforward than some of the previous sections in Chapter 4. But good luck studying, everybody, and I'll see you next time.